Hello there guys, welcome back to another video. Now this is pretty much towards the end of times, isn't it? So make sure that you are fully awake. Make sure that you do fix yourself, because this will be like the last time you'll be fixing yourself. Okay, the last times you'll be fixing yourselves. Okay, and make sure that the future is indeed near, very close. The future is very close. Okay. So you had plenty of time to fix yourself. If there's anything that you still need to be fixed, make sure that you do fix it. Okay, again, there's plenty of help online, and do let me know as well. Okay, so it's time to, if you're not fully awake, it's time to wake up. Okay, all right. Again, if you have not fixed yourself, okay, this is pretty much the last times to fix yourself properly, and the future is here. Okay, let's get started. Now, question uh, 1A or 2A in this case. So, energy in a closed system. Now, energy can be created, can be destroyed. So, pretty much energy in the entire universe, in the closed system, the entire universe itself is not changing. Okay, so the answer would be energy. The total energy in the system, in the entire universe, does not change, but energy is allowed to be transferred. Okay, good. Now, this one here, we want to talk about how the students, we need to label how students are able to set up the experiment to investigate which one's better. Now we have large can, small can, sand, and so on, so on, so forth. Okay, now let's take a look what we got. So what we need to do is we need to have at least two diagrams, because we have two things. Now, first of all, we're going to have the this small beaker. Okay, again, we're going to label this. Okay, so this is going to be our small copper can. Now, why am I labeling? Because the question tells me to label it. And then inside of it, I'm going to add some hot water. Okay. Now, why hot water? Because we want to know which one's an insulator. Now, insulator, it is a material that allows heat to stay in, or allow heat to not be lost. So hot water. Okay. So this will be this one here. And now, how are we going to measure the effectiveness of that? So therefore, we need to have a thermometer placed in. There you go. So this is my thermometer. Okay. Now, I need to use the big container. So this here is going to be my large copper can. Again, I need to label it because the question is telling me to label it. Okay, this here is my large copper can. Now, what's going to happen is in here, I'm going to add my materials. So this here would be my material. So this here will be filled with my material, again, all the way down. Okay, so try to surround the hot water as much as possible with the material. So this would be our material. So this one here could be our sand. Okay, or it could be our, what is it? It could be our sawdust. Okay, so it could be in this particular case again. So what we can do is we can test up, with the sand first, and then we can do the same thing with sawdust. Okay, so draw diagrams again, and stopwatch again. So of course, boiling water, hot water thermometer is there. Stopwatch, stopwatch. Pretty much. There you go. Done. Okay. Now all the marks you get for the pretty much the main diagrams in this case. Alright, let's move to the next one. Now, three factors that must be controlled in this experiment. Now, what we are measuring is we are measuring uh, the heat from the water. Okay, so we want to control how much water we're putting. Okay, now if there's too much water, okay, it means there's more hot water in this case. Okay, so we want to keep, so we want to control the volume of water. Okay, now because what we have is we have the water and then the sand. Okay, and then when we test the sawdust, we want to use the same amount of water in this particular case. Okay, so volume of water needed, and then the amount of amount of material, the amount of sand that we're testing. For example, let's say we used this much sand all the way around, then we need to make sure that we're using the same amount of sawdust all the way around. Okay, so we can't use less or more. Okay, so we can just say pretty much the volume or amount, okay, of sand must equal to the sawdust. Okay, so these two must be the same in this particular case. Okay, and then the third one. Now, what will be the third one? Now, the third one, so it could be the temperature of the water. Okay, now for example, the water, if the hot water is hot, it's boiling water, and if let's say it's 100 degrees, then when you do the test, you want both of them to be at 100 degrees. Okay, and also when you're measuring the time, so the stopwatch here, the stop clock, when you're measuring the time, you want to measure the time for the same interval. Okay, you can, so for example, you measure it every 2 minutes, and then everything should be the same. Okay, so what I would say here is, I would say two things. I'll say that the starting temperature, the initial temperature, okay, of what? Of the water. Okay, so they must be the same for both cases. Okay, right, so that should be enough. Now what we have here is we have using the graph in the figure. Okay, now the question does not say using the data. Okay, so the question isn't the data, so there's no need for me to add the data in. So okay, the question doesn't mention data. The question is telling me use a graph, describe what's going on. Okay, now it's 2 marks. Okay, so pretty much I can clearly see that as density of expanded polystyrene increases, okay, the thermal conductivity of okay, so this is inversely proportional in this particular case. Okay, now if you do use nonlinear, and the masking does allow that, but you want to be safer. Okay, you want to be on the safe side. Okay, so inverse proportional in most contexts is allowed, and well, in this context, if one's going up, the other one's going down, then inverse proportional is fine. Okay, now this is crossed out. We don't need to know that. Now here we go. Now this is the one that many people, I was surprised that people got wrong. Okay, so this is the question that we need to wake up. Very easy question, guys. So what we have is we have a tracer that is used when scanning a person's kidney, and the kidney is inside your body. Okay, is inside your body. Now, for those of you who do biology, you know this better than me. Now, it even tells you here that the isotope, the reactive isotope, is injected inside the person's body. Okay, now the isotope is going to emit radiation, and then it goes through the kidney. Radiation is detected outside the body. So what you have is you have the full nature of the guy laying around. Okay. Okay. Now here you have let's say you have a detector here. Okay. Now the guy, kidney is there. Okay. Now what's happening is the substance goes into the body, is injected, and then this is going to be emitted. It means it's going to go through the organs, the tissue, and then the skin will go to the detector. Now the question says which radiation will be emitted. Now the radiation that must be emitted, so the radiation that must be emitted, it must have a high penetrating power, because it should be able to go through, okay, because it should be able to be detected outside the body, okay. Now alpha is high ionizing. Alpha is highly ionizing, okay, means, and then it's going to have a low penetrating power. So the only one option is going to be D. The only option is going to be gamma radiation in this particular case, okay, because gamma has the highest penetrating power, so they're going to be go. Now this one is going to be stuck in. Now even beta minus, the electrons, can be stuck in to the body, and they are going to be dangerous if they stuck into the body, okay. Now this one was fine, so why is it not so? Okay, so technician needs to take a reading for 30 minutes. So pretty much you need to stay there for 30 minutes. And the half-life is about 6 hours, okay? Alright, now why a half-life of 6 minutes is not suitable? Because what's going to happen is, okay, so if it is 6 minutes, okay, 6 minutes, so isotope 6 minutes, it means that the isotope is going to decay, the isotope is going to decay too quickly, okay, to take any reading, okay, because the guy is going to take reading for 60 minutes, yeah, 30 minutes. So by the time they take you from, let's say, whatever they inject you to from, okay, and then they take you to the scanner or wherever they're scanning you from, it's already too late. 6 minutes gone. Now why is 6 days not suitable? Okay, so if it's 6 days, that's gonna stays in body too long, okay, and the problem there is that it could cause damage to your organs. Yeah, it could cause damage to your organs, right? We don't want you to stay too long, okay. Now what is the risk? What is the person can do? Okay, now the person, first of all, the person can wear protective clothing, okay. Now, for those of you who unfortunately broke something from your body and you had to go and get yourself scanned, you'll notice that the guy is wearing something, okay, wearing protective layer. And also you'll notice that the person is going to be using some sort of shielding, okay. So it means, what this means, that the person is going to be standing behind a barrier or a screen, okay. So behind a barrier, okay, so the person going behind a barrier, okay. Now also what you want to do, the third thing is here, because you want to reduce the risk of the technician want to reduce the risk, and what happens is they will use a shielding. And now if the shielding is not available, what they will tend to do is they will tend to get out of the room, okay. So what they want to do is they want to limit exposure time, okay. They want to limit exposure time, and also they want to limit, they want to, stay as far as possible, okay. Now the clothing could be gloves, they will wear gloves, okay, and then they can use like tongs as well, okay. Now unfortunately the mask scheme does not allow mask, okay. The mask scheme says ignore goggles, okay. So ignore goggles, okay. Now why ignore goggles? Because here what's happening here is the radioactive stuff is inside the patient, okay. Now so the stuff is in the patient. Now the goggles will do nothing. So what you want to do is you don't want to stay close to the patient for a long time, okay. You want to wear some clothing, okay, alright, and then you want to be shielded in this case, okay. Now this is a good question there, very nice question. Again, I'm surprised that people mess this up again, so this is another one we need to wake up. Now why pushing the control rod? Now the control rods, what does it do? Now, the control rod is going to absorb, okay, excess neutrons. This is the one going to absorb. So going to absorb excess neutrons. Now, what does this do? Now, by absorbing excess neutrons means you're going to have less neutrons available to start another fission reaction. Okay, these are the two marks. The first mark you need to say they can absorb the neutrons, and then how will it reduce, how will it slow down the chain reaction? Because if they absorb excess neutrons, means there's less neutron available to start the other one. That's how it's going to slow it down. Absorb neutrons, therefore there's less of them available. Okay, good. Right, now this one's straightforward. This one's just like basic maths there, guys. Okay, so what's the average speed of slow of the average speed, and so on and so forth. So therefore it is the slow on the top divided by the fast at the bottom. The question tell you already, and percentage, where is it? Percentage, 100%. Use the calculator, and you get something about 0.013. Okay, now here's a question that people also messed up, so this is the one we need to wake up as well. Now, nuclear reaction, first place, blah blah, generating electricity. What happened next? Now, what we have is we have the reactor. Now, the reactor is going to heat up the water. Okay, so the heat from it, so the heat is going to heat up the water. The water is going to turn steam, and steam is going to do what it needs to do next. Now, there's 2 marks. So, what is the next step? And the next step is the following. So, what we have is we have the neutrons. So neutrons, they are fast. Means that they're gonna have kinetic energy. Okay, and that kinetic energy is going to go, okay, transferred to heat energy to heat up the water, to heat up water into steam. Okay, and the next step in terms of energy transfer is the kinetic energy of the fast moving neutrons is transferred to heat energy or thermal energy, because we need to heat up the water into steam. That's it. Okay, that's it. That's what we need to talk about. Okay, that's only 2 steps there. Okay, that's the next step from the nuclear reactor. Okay, so hopefully this helped you out and fix yourself in this particular case. Okay, let's move on. Skip this one. Okay, this one was fine. This one's okay. So this one was all good. This one, Big Bang. Everyone knows Big Bang. Okay. Now this one was also easy, nice and easy. Okay, so now you need to show it is about this. So what you do is you put numbers in, and then you get the answer you get to be 0.04. Okay, so this is the one that you need to show. Okay, so you calculate, you put your numbers in, and then you need to show that it is 0.024, which is about this one. So okay, so you get the mark to show that it is about, not exactly about. Now this was okay. This one's also straightforward. Again, so put numbers in. Okay, and then you get put the numbers in. The numbers here. So this is C. Okay, and then V. This is the one that you calculated. Okay, so pretty much it is 3 times 10 to the power 8 bracket times 0.024. You can use 25 if you want, and then you get, so 1, 2, 3, 4. Yeah, so you get around this number here again. So if you get 73 something, is also correct. Yeah. Okay, good. Now let's take a look at this one. So this is the one that people tend to mess up. Now, the wavelength of the X lines measured for a distance was about this much. So this is the wavelength. Yeah, that's the wavelength. Now, how does this show that the universe is expanding? Now this is the wavelength. Let's take a look. So this is the wavelength measured. Okay. Now, okay, 0.4, yeah. So this is the wavelength measured. Let me take a look at this one again. So it's 0.92. 0.92. Okay, so the wavelength of the spectrum line X measured for wavelength. Okay. Okay. And then the wavelength here is this much. Okay. Now there are two things that we need to say. What has happened to the wavelength? Now, first of all, okay, the wavelength has increased. Okay, so we notice that the wavelength has increased. Okay, so the wavelength has increased. So the wavelength on see how the wavelength on Earth is 6.56. Okay, and the wavelength that measured was 6.92. So the wavelength has increased. It got larger. Okay, now what does this tell us? Now this tells us that the galaxy is moving away from who? From us, okay, at a faster pace. Okay, it is moving at us. It's moving from us at a faster pace. Okay, quicker. All right. Now, how do we know if it's quicker? Because what we do is normally astronomers, they're going to use this equation here. So this is the velocity, the recession velocity, the velocity at which they are moving away from us. So what we do is they use z is equal to c times v. So right. So if we do this, and then we get put this in. Okay. Now this value here, so this number that we get, okay, is going to be higher than this one here. Okay, so this is the one we calculated. It's going to be higher than the one we got. So, okay, so Z, where's Z? Yeah, again, we need to do this. Yeah, so we need to do this. All right. So when we do this, so this is wrong. So we need to put the velocity in there. What's the velocity? Okay. So if you use this, to work out the Z, okay, which is the Z in this case, that's the redshift. The redshift. Okay. So the Z is the redshift. And Z is put Z there. Now we notice that this number here is higher. So it means that it's going to getting away from us faster. Yeah, faster. That's the thing that we need to remember. Faster. Okay, this is the thing people messed up. Faster. Okay, now why? So okay, so first of all we got the Earth. Yeah, the atmosphere. Satellite. Okay. Now question is why some satellites are located on satellite in orbit, so we can have a telescope here. Okay, why is it there? Okay. Now first of all, the first mark that everyone got correct was there's less interference. Okay. Now interference, this could be the dust, this could be cloud. Okay, this could be light pollution. So this is interference, yeah. Okay. This is interference. Okay. Now what's the second one? The second one means what happened is sometimes the wave coming from outer space, okay, get absorbed by our atmosphere. Okay. So what we need to say, some wavelength absorbed by atmosphere. Okay. Alright. So therefore, by having the telescope in orbit or on the satellite in orbit, so it means that the wave that's coming up can go to the satellite and we can get it. Okay. Alright. Now there's nothing to do with closer. okay, because the space is so big. So if I draw the Earth here, and if this is my satellite, so this is my satellite, then the sun, okay, now the star is so far away that it's like a dot. So this here could be a star, and look how far this is. Okay, look how far this is. This is how far this is. Okay, so even this distance does nothing. This distance here does nothing. Okay, so it doesn't matter about the closeness. Yeah, it does not. The telescope is closer to the object in space is wrong. Okay, so this is very far away. So these are the two reasons why. Now, if you want a third reason, I'll give you a third reason just in case. Okay, third reason. Let's take a look. Third reason. What can we say? Third reason. Okay, third reason is you can view the entire sky. Okay, it means that this here can see everything. So you can see everything, everything all the way around. It's 360. Yeah. Okay. Good. Let's move to the next one. Now momentum. This is momentum. P is equal to mass times velocity. Mass is kg. Velocity is meter per second. So therefore it's going to be b. Oops. Wrong. It's going to be a. Again. So be careful. Take your time. So take time. Take time to fix yourself. I just fix myself. Again, so close this one. So the answer is a kilograms meter per meter. Okay. Now this is a nice question. Okay, let's take a look. What can we do in this case? Okay. Now a few things we can do. Students blah blah carry out momentum is conserved. Okay. Okay. Now what diagram tells? Okay, momentum conserved. What does it tell you? Momentum. So it tells you that total momentum before collision is equal to total momentum after the collision. Okay, so what you want to do is you want to find a way to work out. So what we're going to do, okay, this is A and B. All right. So, let's say trolley B is at rest for stop. So its momentum is going to be mv. So the v is 0, so therefore it's going to be 0 kg meter square per square, isn't it? Okay, so we keep it simple. We say, okay, this is not moving. Make our life easy, isn't it? Now this is moving. So now why do we raise? We put it on the block, so this way it can go down. So gravity can put it down if you want to do that, and so on and so forth. Okay, now how can we work out the speed of this? Now speed is the distance is traveled, okay, over time. So what we're going to do is we're going to say what is it? We're going to say find speed of trolley A. Okay, now how can we do this? Distance, the distance covered, okay, the distance covered, okay, alright, over time taken, over the time taken to do what? Over the time taken to, let's say, over the time taken to reach trolley B. Now how can we get the distance covered? So we can use a ruler here. How can we get the time taken? We can use a stopwatch. Now you can use like light gauge if you want to do that. Yeah, you can talk about light gauge and so on and so forth. Yeah. Okay. Alright, and then what we need to do is we need to, the mass, we've got, because this one's straightforward because there's no mass there. Okay, so measure mass of trolley A with imbalance. Okay, so trolley A, the moment go to this, so this will give you the moment. Okay, okay, now you know the mass of the trolley A. Now you know work out the velocity or the speed already. Now you can work out the momentum. So therefore, total momentum before the collision is equal to, so momentum of A plus momentum of B, isn't it? Okay, and then we need to do the same thing afterwards. Now, how can we make our life easier? Let's take a look what we say. How can we make our life much easier? Now, they are identical, the mass is the same. And how can we make it easier? So what happened is, so when, after the collision, we're going to say that A, so look, the sticky pad there, A and B stick together and they move together. Let's say that. Okay, so therefore, right, so trolley A, stick, trolley B. Alright, so therefore, what we need to do is we just need to measure. So we're looking for the final velocity, we just need to measure. Okay, so measure their combined velocity. Measure the combined velocity. Okay, now how did this look like? So what we say is, I'll show you how it looks like. So total momentum after the collision. Now after the collision, we know it's going to be momentum A plus momentum of B. Now momentum is going to be mass times the velocity plus mass times the velocity. So plus mass times the velocity. Now the mass is the same. Now the mass, the velocity of A and the velocity of B, okay, we're going to combine them. Okay, so we're going to combine them together because they stick together, so they are moving together. Okay, so we need to determine this one. How can we determine this one? It is using the same method in this case. Okay, now they stick together, they move together, so we see how far they moved with the ruler and how long it took for them to move that particular distance, and then we get the speed. Okay, to combine them together. So what we're going to have is we're going to have just combine them together, and then what we need to do is put the numbers into the equation. Okay, so using I'll call this number 1. Okay, using number 1, check if same value. Okay, so you got momentum before, momentum after, you just check them whether they're the same value. And of course, it's 4 marker questions. Yeah, we'll leave it there. You can talk about repeat and take an average and so on and so forth. Yeah, we're going to leave it there. Okay, man, because there's only 4 marks. Okay, but we need to get all the marks. Yeah, just because we leave it alone to mean anything. Now, give a reason why it has to be slanted. Okay, now slanted. Now friction is always there. Okay, now friction is going to always be friction. Okay, now it doesn't matter if it's very slanted, so like this, friction will still be there. Okay, now what do we want to do? Okay, what do we want to do? Okay, so what do you want to do? Now, one thing you want is remember. One thing, think of it logically. Yeah. Now, if the object is here right now, so if the object starts to move, okay, it can move, and then you can stop. You can move a little bit and stop. Okay. So what we want to do is we want to lift it in a way so when it moves down at the same speed. Okay. So we want to make it move. Okay. So Control A, moves at the same speed. So we don't want it to like go like f. So for example, if it's like of being at the slope, okay. So if it's flat, it's not going to move. Sorry, if it's flat, it's not going to move. So we have to move it, and sometimes we can move it fast, we can move it slow. Okay. Now friction, reducing the effect of friction, Okay. So the second option that the Muslims say is reducing the effect. Now the word effect is in bold for some reason of friction, because friction is always there, but they want to reduce the effect of it. So this will allow the trolley to move at the same speed. Okay. Now this one's an easy question there. This one, guys. Okay, you just put everything into the number 0.05. Now which one? Look. So which one's the final? Which one's the initial? Okay, so now only you guys will know this one. Which one's the final velocity? Which one's the initial velocity? Okay. Now this here. So this is the initial velocity. This here is the final velocity. Okay. So what we have is we have the final velocity minus the mass times the initial velocity, bracket, the whole thing divided by time. Now time, looks, this is millisecond, so therefore we need to convert this, and then we will get something about okay, so this is the answer there. Okay, now if you got this wrong, then write down, so this here is, so 15 is final velocity, this is initial velocity. Okay, now Newton's third law, you guys know this. Okay, so forces are equal and opposite. Okay, now for example, if I have an object A, this object A exerts force on an object B. Now object B is going to exert an equal force but in the opposite direction. Okay, so on different objects. Okay, so this is Newton's third law. So this is what's happening here. Okay, so you have, what is it, collision between the ball and the racket. Okay, so the racket is going to be exerting a force on, so the ball is going to exert a force on the racket, and then the racket is going to exert an equal and opposite force on the ball in this particular case. Again, so forces are equal and opposite, so this is Newton's third law. Okay, okay, this one's crossed out, this one's crossed out, this one's easy. Okay, this is easy one. Okay, so the frequency, what happens, so look, increases. Okay, which one is dangerous? Remember, electromagnetic waves. So radio wave we use, radio wave has the lowest frequency, so therefore the frequency, the bigger the frequency, so high frequency means there's more waves, so the dangerer it gets. Now equation you need to remember, wave speed is equal to frequency multiplied by wavelength, and you're looking for the wavelength, so wavelength is velocity over f. Speed, you know, 3, the question tells you, make sure that you write it properly. Now this here is giga. Now giga is times 10 to the power 9. Again, now how do we know? Let's say you forget. So gigas, so you go kilo, you go up, you have mega, you go up, so this mega, this kilo, and then you have giga. Okay, now how do you know how many zeros you have? Let's do it this way. Now kilo is 3 zeros. Now mega is 3 extra zeros. Giga is going to be 3 extra zeros. Again, extra. Here you go. That's how you remember it. Okay. So therefore, 2 power 9. Again, use your calculator, and this you get something 0.12 in this particular case. Okay, make sure that everything is indeed sorted out. Good. Okay, efficiency. Now you guys need you have the equation sheet. Efficiency is going to be useful over total. Okay, and this is the percentage. So percentage. So this is going to be this one here. We're looking for what we're looking for total. Let me rearrange this first. So total is equal to useful over efficiency. Now the useful oven is this, transfers this to some food when it's heated, so therefore it's going to be this much divided by efficiency. Now efficiency, we need to turn this into 0.55. Okay, we get this much. That's the total energy. Okay, now the total energy must be bigger than the useful energy. That's how you know if it's correct. Okay. Ooh, okay, this is the last. Yeah, that's the last one. Now this is a good one. It's the good one. Now, how can we do this? What I'm going to do is we're going to do it this way. So first of all, we'll talk about the uses. Okay, and the different ways: comparison, comparison, comparison. Okay, comparison. Okay, and different ways they involve you producing. Okay, so producing, making. Okay, and then we have X-ray, we have radio. Okay, now if we want to get some marks, okay, even though we forgot a few things about these guys, always start with the easiest one. Okay, always start with the comparison. Now you know that X-rays has high frequency. Okay, you know that radio has low frequency. You know that, isn't it? You know that this guy's got short wavelength. You know that this one has very large wavelength. Okay, now we're comparing them, yeah? Okay, now 2, fair enough. Now let's move on to the uses. Now radio wave, you guys know TV, isn't it? Radio, isn't it? Mobile phone. X-rays. Let's say medical uses, medical diagnosis. Okay, it could be bones, blah blah blah. What else? Airport security. Airport security. Okay. Yeah. Okay. Now let's talk about the production in this particular case. Okay, the production is the one that people tend to forget. Now, electrons. Okay. Now this is a little bit tricky. Okay, because it's something that I may think that this question is outdated. Just check you up now. Question tells you that the electrons, X-rays, are emitted when electrons within the atom go through energy changes. Now, what happened is, okay, so let me draw an atom somewhere here. I've got the atoms, I've got the shells going around, one shells, let's say two shells. Okay. Now, what happened is the electrons in the lowest energy level here is going to gain energy, and when you gain energy, it's going to go up a levels, isn't it? Okay, going to go up a levels. And what happened is, and then it's going to lose that energy, and it's going to drop back to its level. Now, when it does that, when it go up, absorbing energy, and when it loses energy, it goes drop back down again. So energy is, when that energy is being lost, that energy is turned into X-rays. Okay, that's how this works. Okay, electrons in lower energy level or shells, okay, absorbs energy, okay, move up level, okay, then turn back right? The electrons loses that energy in form of, let's say, X-rays here. Okay, so the X is very high energy in this particular case. Okay, we're gonna keep it there. Now we go down. How about radio wave? Let's go back to purple. Radio wave. Now radio wave is, you guys know, okay, so it goes by, what is it, right, how does it go by? Also, so let's take a look. Electrons in seconds. So what do the electrons do? Okay, so electrons, oh, I thought I should change this. Electrons, what do they do? They oscillate in seconds. They oscillate in seconds. Oscillate in seconds. Okay. Now let's go a little bit more details, just for your sake. All right. Just for your sake, yeah. Now what happens is, let's say we have the antenna, the radio antenna. Okay. Now the electrons in the antenna is going to oscillate. It's going to move up, and then it's going to move down. So go up, down, up, down, up, down, up, down. So it means that when it oscillates, what we end up getting is we end up getting an AC current being generated. Okay. Right. So because the electrons oscillate in the electric circuit, so we have an AC current that is flowing in the antenna. Okay, and this generates the radio waves. Okay, now we're going to leave it there because this is most the last of the questions. Again, make sure that everything is indeed fixed up. Okay, energy questions and so on and so forth, so you know, guys, what you need to do. Now again, make sure that you keep doing more practice questions, yeah, so do not leave anything to chance. Okay, so the more you get yourself covered, the better it's going to be. Okay, otherwise, you know,